my last video is going to be about springs and about power, and I'm going to try and work through this pretty quickly. Okay, springs. A string has a natural position where at rest, it's slightly distended. You can compress it, which is doing work, or you can stretch it, which is doing work. But a spring in its natural state is just kind of a coil that has a little bit of spacing between, and you're going to get my son in this video too. Okay, so when you take the time to actually press on the spring and compress it, it's doing negative work because you are going the opposite direction the spring actually wants to move. All right, at rest, that rest position is just the loose, unmessed with spring. Now, on the other hand, if you hang something or pull on that spring, sorry, baby, when you pull on that spring, you're also doing negative work because you're working against the movement of the spring. Because as soon as I would release it, it would go back to that normal, relaxed state. Same thing. If I press it in, unless it's a slinky, if I press it in, as soon as I release it, it would go back to its relaxed state, about whatever the distance of that spring is. So anytime you push it in against its natural state, it's considered negative work. And when you stretch it, it's doing negative work because that's against its natural state. And that motion to get back to its natural state is the positive work. So when you stretch it and you release and the spring comes back to its natural state, the motion from the stretch to natural state is positive work. And it seems counterintuitive, when you compress that spring real tight and then you release it, that movement from the compressed state to natural state is also considered positive work. So when you compress it, that's considered negative work, that pushing it against what it wants to do or stretching it against what it wants to do. Okay. Now, the equation for spring, the work done by a spring, is 1/2 the spring constant, which is K, times x squared, which is the distance it's pulled. Okay? So, work done by the spring, as usual, is considered joules. And the spring constant is a Newton meter, the amount of force per distance. So another way you could look at that, like we've talked about, replacing one letter for another. Like before, we were replacing force we would replace force with mass times gravity, or mass times acceleration. Now we're going to replace constant, if we need to, with force divided by distance. Okay? Now, x is the displacement. The displacement is the distance that spring traveled to get out of whack, all right, to either be stretched or compressed from its natural length. Okay, we talked about the equal work, or the positive work. That's when it's moving back to its natural state. Okay, work applied. So when you're applying a force, when you're pressing it or stretching it beyond its natural state, that is applied force. So that's a negative spring. All right, when it's moving back to its state, that's positive. So we're going to always, when we're stretching or compressing a spring, it's always, notice that negative that's put here. That's why, because it's going against its natural state. Okay. Okay, so here's a spring in its natural state, right? It's just perfectly happy sitting where it is. Well, then we pull that box a given distance. Here's our displacement. This is working it against its natural movement, okay? So the force of the spring is going to pull it back to get it back to this happy state. It's its happy place, right? So Hooke's law states that the force on the spring is the negative spring constant times x. So you're going to need that later. Okay? So that's how you determine the force. The greater the distance, the greater the force you're going to have to apply, which is kind of obvious. Like if you're really pulling on a string, you really are working it. All right? Same with if you're really pushing on it, you're applying a lot of force. The more you push, like the more you compress the spring or the more you stretch it, the greater force you're going to have to apply. Okay? And then the work is this is a negative area. Like we are applying negative force. The once it returns, once it does this displacement, this is a positive displacement because it's going, again, back, think it's going back to its happy place. Okay, so, but when we're stretching it out, when we're moving in this direction, it's going to be a negative space. Okay, so now you are going to have to do work equals -1/2 kx squared. Okay, each one of these is going to be the same. And there are people here, so I'm going to pause. Oops. Okay, I don't know what I did. It's going to get busy here in just a sec, so I want to try and power through this. Okay, now, this time we have work, and we have a distance. What is the force? Remember we talked about F equals negative, oh shoot, backtrack. F of spring is negative K times X. So in this one, negative K times X, you're literally, I like to say, plugging and chugging. So to compress a certain spring, so if it takes, oh, hang on, we have the work, this time we have work, and you have distance. Work is 1,000 joules. Oops. You have distance, which is 0.10 meters. We have work, and we have distance. So we're going to have to first strike that. We're going to have to first say work equal to 1/2 -1/2 k x squared. So now we know work is 1,000 joules. You're going to have to work backwards. Equals -1/2 k, and this is what we're trying to figure out, the constant times 0.10 meters, right? So you have to solve for k. So multiply both sides by -2, cancel that out. So the first thing we'll do, multiply by -2 by -2. Now we're going to have 2,000, -2,000 joules equals k 0.10 meters squared. So square that, and then divide both sides by 0.10 meters squared. So take the time to square it. I'm not pulling out a calculator right now. Divide this by 0.10 meters squared, and that gives you your constant. Okay. To compress a spring an additional 0.10 meters, does it take so this time you're doing well now this time you're going to redo this, but you're going to replace it with 0.20 meters because you're doing an additional. So go ahead, work through that same calculation we did here, down here, and make sure you show your work. Good. How much work is done by the force shown when it acts on an object pushing from 0.25 to 0.75? So again, when you're pushing, you're ultimately changing that to 0.5 meters. So calculate that out, show your work. Okay, again, figure out your change in displacement. What is the change in displacement here, and calculate for it. Okay, so figure out how much work is done using that same equation. Okay, finally, power. So we'll get real busy. Power is the rate. So I have a really great video by the flipping physics guy. He's a little bit strange, but I think he explains it well and shows the process of how you get from one equation to another. So please watch that video as well, and that will count as some of your time. But I will explain it as well. I just don't have all the fun animations and the participation component. All right, power is the rate at which work is done. Okay. Work is done in joules, and this change, remember this is change in, we've seen it like a billion times. This is change in. Change in time is done in seconds. So when we run upstairs, P is small, so P is big. When we run, you get up the stairs quickly, but the power is big. You are going to actually have to do this. I'm sure all of you have stairs abouts. You might look silly measuring the stairs, but that's the final lab that will be part of your test or your assessment. Okay, When we walk upstairs, P is large, so the power done is little. You've done the same amount of work to get up the stairs. You've just extended it over a greater amount of time. All right. Unit of power. Power is 1 joule per second, 1 watt, and it's measured in watts. So you'll notice like your lights are measured in kilowatts. So there's 1,000 kilowatts to 1 watt, or there's 1,000 watts to 1 kilowatt. I apologize. So that's one. So 1,000 watts is equal to 1 kilowatt. Okay. And it's named after the engineer James Watt. He perfected the steam engine, and he also, like in the past, they had done everything by horses, horse and buggy. So, well, hello, he's bringing. There you go. So, thanks, baby. Okay, so when he made these conversions, he had to convince people, like, hey, this steam engine is going to do more effective work than if you were to use a horse. So he had to compare it to a horse. So you'll see in flipping physics, he explains it as well. They come up with an arbitrary number for horsepower, but when you hear about like cars, you talk about the horsepower. That's where that came from. It's just there's horsepower or wattage. You could convert the horsepower of your car to watts, but we don't do it that way. Okay, so here you go. 1 horsepower to 746 watts. Okay, so if you think you have a 60 kilowatt light bulb, which are the standard light bulbs, they're putting out a lot of horsepower if you do that calculation. Because if you have a 60 kilowatt light bulb, which is equivalent to 60,000 watts. So 60,000 watts. Oh, G-Bug, please stop. Okay. 1 watt is, no, 1 horsepower is 700. Hang on, I lost my 746 watts. I can calculate that. How much horsepower is 746 watts? How much is that going to do? Quite a bit. He's fun. He's learning physics. Okay, so how we buy energy? Kilowatt hour. All right, so that's how power companies record the energy you get. But it's not energy consumed, it's just energy moved from the energy department to the lights in your house, right? Yeah. My son Gerald says, yeah, that's what it is. 1 hour is equivalent to 3,600 seconds. So 1 kilowatt hour is 1,000 joules per second times 3,600 seconds. So there's your equivalency. So you're going to have to do this on the power lab. Go through and work this out. If you need help, we can work through it. But use the equations we have. But I'm starting to run out of time. Okay, try this one as well. Don't forget grams needs to be converted to kilograms and centimeters should be converted to meters. Okay, force types. Forces acting on a system, they can be divided in 2 types. There's conservation, where and non-conservation, when things get released. Okay. Work can be calculated from start to ending point. The actual path is ignored. Oh man, if starting no horse. Work changes the potential. Okay, if the starting point and ending are the same, no work is done, and it is potential energy. So gravity, spring forces, like when they come back to normal or when they land. Okay. Non-conservation. Path is dependent. Knowing the start is not, you're not able to calculate it. Work along a closed path. So I'm skipping ahead. That's friction, drag. So that means there's something else playing here that you need to pay attention to. Okay, I'm going to have to cut it here because they're going to kick me off. Talk about the last one shortly.